ladies and gentlemen. We're going to do 9.3a today. We're going to be talking about the integral test. So our objectives are that we're going to use the integral test to determine whether or not an infinite series converges or diverges. So here is the information for the integral test. It does have some criteria that must be passed first. So if a function is positive, and don't forget that that means it's above the x-axis, it is continuous and decreasing, and the terms of the sequence are equal to the function evaluated at the address, then the summation from n equals 1 to infinity of a sub n and the integral of 1 to infinity of f of x dx either both converge or they both diverge. So what we're going to be doing for the rest of this chapter are different tests that can be applied to infinite series to determine whether or not they converge or diverge. And I am going to apologize for your video being late. I will explain that to you tomorrow, if you really care. So the book does a really interesting proof. And I know you guys don't get super excited about a proof, and I was going to include it, and then I changed my mind and decided not to. But I think that it helps to illustrate a point. So instead of doing the whole proof, I'm just going to show you, a little bit of information to kind of clarify this portion right here. So let's say, and you can look at the whole proof in the book, it's actually fairly entertaining. So here is going to be my function f of x, okay, and then I'm going to either inscribe or circumscribe some triangles, and at this one I'm just going to circumscribe, okay, and then so now I have my rectangle circumscribed on the original function, and this would be 1, 2, 3, 4, dot, 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 and then this would be this point right here, n minus 1, and then this would be n, okay? So if you'll notice right here, a sub 2 is going to equal f of 2, okay? And then I'm going to squeeze it up here. A sub 1 would equal f of 1. Okay, and you can see that the y values would be equal to the function evaluated at the sequence position, and then I could go all the way out to the end. So, and the situation is slightly different whether I circumscribe or inscribe, but this is going to be the information that we use to prove the integral test. And so basically, I'm going to have my circumscribed rectangles, except I can't spell, my circumscribed rectangles and my inscribed, gosh, I can't spell to save my soul today, inscribed rectangles would give me an evaluation of the sum of the terms, or the sum of the rectangles, and then after we went through a bunch of the proof, we would get that the sum from I equals 2 to n of f of I would be less than or equal to, and this is the inscribed, and I'm not going to show you the whole proof, just a couple of pieces, is less than or equal to the integral from 1 to n, of f of x dx, and that's going to be less than or equal to the sum from I equals 1 to n minus 1 of f of I. And this is the circumscribed. So basically, what this says, and if you read through the proof is actually fairly interesting. It says that the inscribed, which would be, underneath, we'll just make those guys purple, and then I would have this one, and then this one, and this one, and this one, okay, nice straight line. The inscribed sum of the individual rectangles is slightly less than the actual sum, which is a little bit less than the circumscribed. So that says that the actual sum from 1 to n is going to be somewhere in between these two summations. Alrighty, so notice that the criteria have to be met. We'll just go back over it. F has to be positive, continuous, and decreasing. And then if that's true, then I can apply the integral test. So I think the easiest way to do this is just to start with an example. So let me scoot my paper up so you might be able to see the example and scoochie it over. All right, so for our first example, it says apply the integral test to the series. And the series that we're going to have is the sum from I equals 1 to infinity of n over n squared plus 1. So before I go on, I kind of want to go back to here. Notice that I have f of x dx, and I have the integral from 1 to n. Basically, that's the second fundamental theorem of calculus. And so that's how we're going to manage our variables. So what I'm going to do is I'm going to say that f of x is equal to x over x squared plus 1. And I want to know that the function is positive and continuous. So I could actually look at the graph of this, and if I do, and I didn't write it down, so I'm kind of drawing from memory, I think it does something kind of like this. That goes out to infinity. There's my little arrow. There's my little arrow. This is gross. I think this is a 1, and this is a negative 1. It does cross at the origin. So I can see that my function is positive, meaning it's above the x-axis. It's barely above the x-axis, but it is above. And it is continuous for x is greater than or equal to 1. Because remember, we're also talking about starting our summation at the first term, which is why I want to look at the function when its x is greater than or equal to 1. So if I want to talk about my function, and I want to know, if it's increasing or decreasing, I need to take the derivative. So f prime of x, because it is the quotient rule, is going to be low times the derivative of the high minus high times the derivative of the low, all over x squared plus 1 quantity squared. So there's my derivative. If I simplify and clean up my derivative, I'm going to get 1 minus x squared over x squared plus 1 quantity squared. And this is my derivative. And I want to set it equal to 0 so that I can solve. Sorry, I am just dying over here. And so if I cross multiply, I'm going to get 1 minus x squared is equal to 0. A negative x squared is a negative 1, x squared is 1, and x is going to equal plus or minus 1. So from the first derivative test, those would be my critical points. But primarily, I'm interested in what happens after that. So what I'm going to do is I'm going to evaluate my derivative. So this is going to be f prime of x, and I'm just going to look at 1. So I'm going to substitute in 10. So if I do f prime of 10, I would get 1 minus 100 over 100 plus 1, so 101 quantity squared. This guy's negative, this guy's positive, so this is negative. So that means that my function is decreasing. So f of x is decreasing for x is greater than or equal to 1. Okay, so now we have satisfied the 3 criteria for the integral test, which was that the function is positive and continuous. Remember, this is continuous because I would only have imaginary numbers in the denominator, and imaginary numbers don't show up on our real number line. I took my derivative and I evaluated it for x is greater than or equal to 1, and I found that it's decreasing. So now I've satisfied the 3 criteria for the integral test. So now what I'm going to do is I'm actually going to apply the integral test, okay? So here's my integral test. Make sure you can see, almost can see, okay? So I am going to have the integral from 1 to infinity of x over x squared plus 1 dx. Alrighty. And so I'm going to let my u equal x squared plus 1. My du is 2x dx. So I need to introduce a half. And so this is going to be 1/2 the integral from 1 to infinity of 1 over u du. So now I'm going to take this into limit notation. So this is 1/2 the limit as b approaches infinity, and then I have the integral from 1 to b of 1 over u, oops, that's supposed to be a d, u, oops, that's a u, whew, brain cells are a little fried. So when I do that math, I get 1/2, and then I have the natural log, and then I have absolute value x squared plus 1, and I am going to evaluate, I'll put it like this so it's a little bit easier, from 1 to b, okay? So then this becomes 1/2, and then I have the natural log of b squared plus 1 minus the natural log of 2. This is going to approach infinity because this is going to increase without bound. So that means that my limit approaches infinity. And because I'm taking the limit of the series, that means that my series is going to diverge, because it doesn't approach a specific value. So I'm going to write just kind of a conclusion statement. F is positive, it is continuous, and it is decreasing. And when we took our limit, the limit as b approaches infinity of the integral from 1 to b of f of x dx approached infinity. Therefore, the series diverges. Whew, that was a lot of writing. Okay, I have one more example, and then I'm sure we will get to do a lot of these fun problems in class together. So for the second example, we want to do the same thing. We want to apply the integral test to the series, the sum from n equals 1 to infinity of 1 over n squared plus 1. So again, we're going to do the same process. So if I actually convert my function, then I'm going to have 1 over x squared plus 1. Again, I have no vertical asymptotes because I can't have imaginary numbers. And so I'm going to look at the graph. Sorry, you could use your handy dandy grapher. And it does something kind of like this. So this is going to be 1, this might be 5, and then that's going to go on to infinity. I do know that I have a horizontal asymptote at y is equal to 0 because the degree in the denominator is higher than the degree in the numerator. So now I can list my criteria. F of x is positive, it is continuous, and, oops, it is decreasing. And I could have taken the integral and done the first derivative test. If I didn't have access to a calculator, that's what I would have done. So I'm just going to write that over here. Without a grapher, I would use the first derivative test to determine whether or not it's decreasing. So if you don't have access to a grapher, then you would have to run the first derivative test. If you do have access to a calculator, we get to push buttons and yee-haw. So since it is positive, continuous, and decreasing, now I can run the integral test. And here is going to be my integral test. And when we do these types of problems, there are going to be many different tests in this particular process, and so you're always going to want to show which test you are running and then the criteria that allowed you to do that. Okay, so if I run my integral test, I'm going to have 1 to infinity of 1 over x squared plus 1 dx. And because I have to infinity, we're going to replace that with the limit as b approaches infinity of the integral from 1 to b of 1 over x squared plus 1 dx. Okay? Alrighty. And then if we continue, now I need to take my integral right here, and that's going to be the arc tangent. So this is going to be the limit as that's a b, approaches infinity, and then I'm going to have the arc tangent of x, and I'm going to evaluate from 1 to b. So this is the limit as b approaches infinity of the arc, tangent of b minus the arc tangent of 1, okay? And then if you remember, arc tangent goes from, if we talk about this, this is my negative pi over 2 to my positive pi over 2. So the maximum value that b could be would be pi over 2. So then this is going to be pi over 2. The arc tangent of 1 is pi over 4. And so this is equal to a specific value, pi over 4. So since f of x, and I'm just restating this so we kind of see maybe what our solution should look like. It is continuous and decreasing, and the limit as b approaches, approaches infinity of f of x is equal to pi over 4, then we would say that the series converges. Alrighty, so that's kind of it for our integral test. So just to recap, I'm going to write that right here. So here's our recap for the integral test. F has to be, f is our function, f has to be positive, it has to be continuous, and it has to be decreasing. And remember, if you have access to a calculator, then you would just graph it. If you do not have access to a calculator, you would run your first derivative test to determine whether or not the function is decreasing after 1. And then we know the first derivative test, the integral test says, then the integral from 1 to infinity of f of x dx is going to equal, dog's doing weird things, b approaches infinity, integral 1 to b of f of x dx. And this is kind of our second fundamental theorem of calculus, and then we're taking the limit. Alrighty, that is it for today. I will see you soon.